Okay. Yeah, looks good.
Oh, you got it?
Yeah.
Okay.
So, thanks the ASN for the recognition. And I'm also very grateful that as a byproduct of the recognition that as an ecologist, it's my first time traveling to the evolution. As an ecologist, I learned so much about evolution through this very friendly community of evolution biologists. I know I'm the only thing standing between you and the beer, so I'm only going to talk about one project. We see amazing biodiversity out there in nature. If we wander in this hypothetical forest, we may see 3 ponds. In the first pond, we can see 3 fishes. And in the second pond, we see also 3 fishes, but some of them are different. And then suppose in the third pond, we see 5 fish species. How do we measure this biodiversity in this region? One way to do is that if we zoom really close in, only look at the local diversity, or also known as diversity, which simply measures how many species a patch would have on average. So in this case, it's going to be simply 3 plus 3 plus 5 over 3. So the local diversity here is going to be around 3.6. Another way to look at the diversity is if we zoom really out and blurring all the differences between the other patches, we simply look at how many species they have in this whole region, which is also known as gamma diversity. If we are a good fish biologist, you should be able to tell there are 6 different fish species there. However, both the local diversity and the regional diversity ignores the differences among local patches. In a sense, they do not tell us about the diversity of diversity in this patch, which is fulfilled by the concept known as beta diversity. So on a very high conceptual level, biodiversity simply measures the variation among patch compositions in a region. However, unlike the alpha diversity and gamma diversity that ecologists have consensus on how to measure them, it remains one of the most debated concepts in in spatial ecology. For those of you who are unfamiliar with this concept of biodiversity, here I introduce one of the most used definitions in the literature to give you a test of how ecologists have been approaching this question of beta diversity. So this diversity is known as multiplicative beta, which here I simply term as the beta traditional. So it's simply going to be the ratio between the regional diversity over the local diversity. To put it into practice, we can see 2 examples of hypothetical metacommunities. So in these 2 metacommunities, we would both have two species in total, and each of them have 3 patches. So in this first metacommunity 1, the gamma diversity is going to be 2. There are 2 different species. The alpha diversity is going to be 1, since each patch only have 1 species. So the beta tradition is going to be around 2. It's going to be 2. And then for metacommunity 2, we can see that the patch 3 actually has both species present. So now the average local diversity is going to be around 1.3. So it's very easy to tell that using this multiplicative beta, we would assign a higher spatial variation for metacommunity 1 than metacommunity 2. This is not a special property of this beta diversity metric. Actually, proved by Lejeune in this ecology letters paper, all of these commonly used measures of biodiversity would satisfy this criteria. In other sense, we can even call this like an axiom about how people traditionally measure biodiversity. In other words, that biodiversity is maximized when each patch only has 1 distinct species. However, through the extensive ecological research, we know that ecological communities are non-additive. In other words, that the ecology of this patch is unique. In other words, a patch with both species A and B present would behave differently from a patch with only species A or only species B, both dynamically and functionally. Then, with this idea in mind, let's recall about the core principle of beta diversity. It should measure the variation among patch compositions in a region. And in this case, metacommunity 1 would only have 2 unique patch compositions, while metacommunity 2 actually have 3 unique patch compositions. Then, shouldn't we assign a higher biodiversity to metacommunity 2 than metacommunity 1? If you accept this assumption about how we approach this question, then we really need to reconceptualize what biodiversity is. So to summarize, we want to design a measure of biodiversity that would do this. So this is the axis of the value of beta diversity. The minimum value of beta should be 0 when all patches have identical patch composition, so there's no spatial variation. And the maximum beta should be the same as gamma diversity, where we actually see all possible patch compositions possible with a given gamma diversity. And then for all other cases, the beta diversity should be bounded between this 0 and the gamma diversity. So to solve this question, we proposed a geometric approach that would embed a metacommunity as some geometric object living in a high-dimensional space. So to illustrate the workflow, let's just walk through a very, very simple example. So the first information we need is the metacommunity composition. So for example, what are the patches and the patch compositions in each patch? And then we represent this metacommunity composition using equivalent representation as a matrix. So here in the matrix, all the rows are going to represent different patches. So here we have 3 patches, and all the columns represent different species. And the values in the matrix are going to represent the property of this species in this patch. So here, for example, we just focus on the presence-absence data. So in patch 1, only species A is present, so we assign 1, 0. In patch 2, identical to patch 1, 1, 0. And in patch 3, only species B is present, so we 0, 0, 1 in this row. And the crux of our method is to embed this metacommunity matrix as a geometric object living in a hyperdimensional space. So here, now the embedded dimension is going to be the number of species. So here we have 2 species, so we're going to embed this metacommunity matrix in a 2-dimensional space, where each axis represents different species. And then we embed each patch as a point in this embedded space. So each patch has a coordinate, so 1, 0, so it's going to embed it to this point. Patch 2 the same, 1, 0. And patch 3 has 0 and 1, so we embed this point patch into this point on the y-axis. And we also need to embed a ghost patch where no species actually live there. The reason to include the ghost patch are twofold. First, from ecological speaking, including a ghost patch or not should not change the spatial variation. And mathematically, this would allow us to define this geometric embedding for all arbitrary metacommunity matrix. And then we simply, so now a metacommunity composition is translated into a triangle, a geometric object in this embedded space. And then we can simply measure this biodiversity from this formula, where this volume P represents the hypervolume of this geometric object. So this triangle, so it's going to be 1/2 the hypervolume. And we want to normalize it by the number of species there. The reason to do it is by rescaling the hypervolume, we can make it biodiversity comparable across different communities. And then the reason we time the D there is because we want the biodiversity, because the hypervolume always ranges between 0 to 1. So after timing the embedded dimension, it always ranges between 0 to D, so fulfills our design. And then for this specific example, we just need to pull in all these numbers. The hypervolume is going to be 1/2 the area of this triangle. The embedded dimension is D is equal to 2, so it's 1/2. The embedded dimension is 2, so it's going to be 2 times this value, which is around 1.4. And we can see more examples. So this is an example we have already shown before. And then for metacommunity 2, the difference now is that patch 3 would have both species present. So the third law of this metacommunity matrix will be 1, 1, indicating that both species are present in this patch. And then this patch would be embedded into this point here with coordinate 1, 1. So now this metacommunity is no longer a triangle, it's now a square. And this has hypervolume of 1, so now the beta volume is 2, which fulfills our design because we now have all possible patch compositions with a given gamma diversity, and it reaches the highest beta diversity. And then for the case when all metacommunities, or when all the patches have identical patch compositions, we would embed all this patch into the same point, where then we would have no volume for this community. So there's no spatial variation, which also fulfills our design. Now the beta volume equal to 0. And we can do it for beyond this simple 2 species case. We can see it for all possible metacommunities with 3 species. So here on the y-axis, we're going to show the value of the beta volume calculated from the formula before, where the maximum value of the biodiversity is going to be equal to the gamma diversity as designed. And this 1.5 is the minimum non-trivial biodiversity. So as long as there are some spatial variations, it's going to be the minimum. And on the y-axis, we're going to show the number of unique patch compositions. So as we want to only focus on non-trivial biodiversity, so we must have at least 2 unique patch compositions. And the maximum possibility is going to be to the power gamma over -1, so it's around 7. And then we can see that, for example, for this metacommunity with 5 unique patch compositions, each node represents a different patch. The car represents the species. For example, this one has species A and B. This has all 3 species. This one has species B. And this is the corresponding beta diversity. And we can see that for all the possible combinations of the metacommunities with 3 species, we see a very nice linear scaling about how it increases as we add more unique patch compositions. And in addition to that, we also see the variations of beta diversity, even with the same number of unique patch compositions. And this is what we expect. For example, a patch with species A would be more similar to a patch with species AB than to a patch with species BC. So this hypervolume really captures these spatial variations, even with the same number of unique patch compositions. So far, I have introduced the most basic formalism of biodiversity. But given the fundamental importance of biodiversity in spatial statistics, ecologists have come up so many different extensions of the basic measures of biodiversity. Here I just list 5 of them. And because most traditional biodiversity measures are designed in an algebraic way, so all those extensions would require a large modifications on the algebra. However, humans are much better to deal with geometry than algebra. So with the power given by the geometric nature of our measure, we provide, for the first time, a unified framework to define biodiversity for all these applications. Given the time constraints, I'm only going to talk about one specific extension. How do we account for the species similarities in biodiversity? So we know that species similarity should affect biodiversity. So for example, in metacommunity 1, we have 2 patches. One patch has a bird, another patch has a panda. And in another metacommunities, we have against a patch 1 a bird, a patch 2 also another bird from the same family, for example. Then clearly that in metacommunity 1, species are very dissimilar, for example, in their genetics. So we should expect a higher biodiversity in metacommunity 1. Correspondingly, in metacommunity 2, species are very similar, so we should assign lower biodiversity to this community. Of course, here the similarity can mean anything. Genetic similarity, dissimilarity, functional similarity, etc. Whatever of the ecological or evolutionary interests. Then how do we incorporate them here? So let's look at this example, where we essentially assume the privilege that species are totally dissimilar. So in order to study to account for similarity, we introduce a similarity matrix, where all the elements in the similarity matrix indicates how species are similar to one another. The diagonal of the similarity matrix is always going to be 1, because a species is always 100% similar to itself. And the off-diagonal elements are going to represent how similar a species is to another species. Here, for example, we assume that all species are totally dissimilar, so it's always 0 in the off-diagonal. And the cross of the method is to consider the role of the similarity matrix as a new x and y axis. So one of the cases where they are totally dissimilar, there's nothing interesting, because this is originally how we define the 2 axes, the orthogonal 2 axes. However, things would change when we consider the case when species are totally similar. So now the off-diagonal case is no longer 0, it's 1. So if we consider these 2 raw vectors as this new x and y axis, they would be identical. So in other words, that we are compressing these 2 axes into identical points. Therefore, the 2 points here become the same point, and we have 0 hypervolume in this case. Of course, for real communities, they are neither totally dissimilar nor they are totally similar. So for example, we consider species a bit similar. Just as an example, suppose they're like 50% similar. And then in this case, we again consider these two raw vectors as these new axes. We can see now the x-axis becomes this vector, the y-axis becomes this vector, and the hypervolume is compressed a bit. So formally, we can just simply define we need to make only one small modification to the definition. We simply need to consider how much the similarity matrix compress the hypervolume. And we have developed a very efficient mathematical framework to actually account for the similarity matrix, how it affects compress the hypervolume. Okay, so far I've talked about how our measures are different from others. However, we want to highlight that our measure, despite behave qualitatively different from others, it have a strong link to classic measures. In other words, we're really building on the shoulders of those giants. So the classical measures of biodiversity can be classified into two broad schools of thoughts. One is based on information theory, another is based on the variance measure. So out of time limitation, I'm only talk about how it's related to the variance measure. So let's again visit our old friends of this metacommunity with 3 patches, 2 species. This is a metacommunity matrix. And we again embedded it into our 2-dimensional space, patch 1, patch 2, patch 3. And the crux of this method, variance-based method, is to measure how the patch composition is to the mean composition of the whole metacommunity. So basically to the purple one, which is the center of the geometric object. And then the beta variance based measure is simply that the length of this vector, which is around the square root 2 of 2. Note that in Lejean's original paper, he did not propose this geometric interpretation, but we figure it's very, very easy to represent it geometrically. And let's look at another example of metacommunity. So here, we actually have identical patch compositions. However, species A is always 7 times more abundant than species B. And in this case, the embedded geometric object looks something like this. And we can also prove that the beta variance measured by the distance to the mean composition is still going to be square root 2 of 2. However, we can clearly see with our eyes that these two geometric objects are different. And the difference really happens in how these factors are related to one another, which in the language of spatial statistics is known as spatial associations. So in metacommunity 1, there's no spatial association, while in metacommunity 2, there is spatial association. So on a very high level, we will see that the variance-based measure really consider only the first-order information about these factors, while our measure really considers both the first-order information and second-order information, specifically spatial association, that would actually change the qualitative behaviors of the beta diversity measures. Okay, so enough with all the boring theories. Let's see how actually this new measure can tell something new about beta diversity. Of course, in order to apply it to real data, we must have an efficient way to do it. So we have written an R package that will allow us to compute this beta volume very efficiently. It works very fast even for thousands of species. It works very easy. Just load the library, give whatever favorite metacommunity you have, and just call this function beta volume, and you will get this beta volume for the metacommunity matrix. So the first empirical example we're going to focus on is really a central debate in spatial statistics for the last decade, which is about the pattern about beta diversity along latitudinal gradient. So it has been long thought that the beta diversity would decrease along a latitude. So here, the x-axis represents the absolute latitude, while the y-axis represents the beta diversity. So here, I'm just using the traditional beta measure. Each point here represents a different plot. It's clear that we see a declining biodiversity along a absolute latitude. However, in this now classical paper by Nathan Kraft and his colleagues around 10 years ago, they normalized this beta diversity by doing a z-score normalization, basically to control the gamma diversity, and they see no pattern at all about the beta diversity along the latitudinal gradient. We now know exactly that the difference between these two measures is because of the nightmare with the gamma diversity. So here again, x-axis is absolute latitude, y-axis is gamma diversity. Note that it's in log scale, so it's really an exponential decrease of gamma diversity along a absolute latitude. And if we're using the traditional measure of biodiversity, this pattern is fully driven by gamma diversity. While in this measure, it fully forgets about gamma diversity, and therefore you see nothing about it. However, is it possible that we can actually leverage both, not only the gamma diversity information, but also the local information to see how this biodiversity changes? And this is how it goes in our measure. So again, the x-axis is absolute latitude. Y is our biodiversity measure. Each point is a plot. And this is like a unimodal pattern we see. And we know exactly why we will see this unimodal pattern. So this decrease of gamma diversity along a higher absolute latitude is driven by the exponential decrease of the gamma diversity that we'll observe here. While the initial increase of the biodiversity in the lower latitude is driven by the increasing variation of alpha diversity in these plots, which have been largely ignored in the previous studies. Note that we are not trying to claim that this is a true pattern of biodiversity along a latitudinal pattern. There's always a debate on the data quality, etc. But we want to highlight what is important here, that in global synthesis, we always have considerable variation in both alpha diversity and gamma diversity. Thus, we want a measure of biodiversity that would jointly consider the effect of both alpha diversity and gamma diversity. And here we show that now our measure indeed takes both joint effects of both processes in shaping those global trends. And the second empirical application to show here is what I consider to be a fundamental problems in the empirical estimation of the biodiversity, which are about the sampling effect. So here I'm going to use two different data sets which are close to my affiliations. So one is in the KSL site, which is close to Toronto, which is an early successional plots, which is, we know for a fact that is more homogeneous in the spatial landscape. And another is Mont Saint-Hilaire, which is close to Montreal. And we know that this landscape is more spatially heterogeneous. Let's see how the traditional biodiversity would work when we tune the sampling effect. So here we first focus on the KSL sites. The x-axis shows the area we sampled. The y-axis shows different measures of biodiversity. So classical traditional beta measures, the biodiversity measures. Regardless of what measure you are using, it always increases, and increases in a very predictable way. The same thing happens in Mont Saint-Hilaire, where you get the same pattern about how the biodiversity changes with increasing sampling efforts. And this begets two fundamental questions in fieldwork. So first, more sampling does not provide more information. It seems you only need to sample a very few plots, and you can just extrapolate it from it, because it's gives you a very, very strong scaling law there. The second question is that it indeed failed to distinguish the level of spatial variations that we know for a fact there would be between these two plots. And let's see how our measurement works. The x-axis is the number of sample plots. Y-axis is the beta diversity volume. As you can see, initially, there is no distinction between these two sampling sites. However, as soon as you do more sampling, the KSL sites start to have a slower increase. While the Mont Saint-Hilaire keeps increasing. And up to some point, the KSL sites, the biodiversity actually decreases, while the Mont Saint-Hilaire always still increases. And then, with this figure in mind, let's relook at these two fundamental problems in the sampling effect of biodiversity. So now it seems that more sampling actually does provide more information, because if you do few samplings, you cannot tell the spatial difference between these two sites. And second, we can see clear distinction between more heterogeneous areas and more homogeneous areas using our measure of beta diversity. So to wrap it up, the traditional approaches have ignored the non-additivity of ecological communities, essentially that ecological communities with more diverse species actually behave differently from those with smaller number of species richness. And it's very important to consider the patch level variation instead of species level variations across the spatial regions. The second point is that we use a very intuitive geometric way to embed a metacommunity as some object living in the hyperdimensional space. and we can use this hypervolume to quantify biodiversity. And third point is that thanks for the geometric nature of our approach, we can provide a unified framework of biodiversity in various applications. And I'm sure it's also extendable to other cases where of interest. And the fourth point is that our measure indeed provides novel insights to classical problems that have been associated with biodiversity literature for a very long time. So that's it. I hope now you get why my title is called Biodiversity in a Nutshell, because we think now metacommunity is now like a hypervolume object, which is very similar to a nutshell, a theoretician joke. And I will thank all my wonderful collaborators, without whom it's going to be impossible for me to complete this job. And I'd like to thank you guys all for sticking around. I know this is very late, and thank you so much for the time and attention.
So one argument going on right now in community ecology and beta diversity measures is the ability to distinguish nestedness versus turnover. Yeah. So how does your measure distinguish those phenomena?
Yeah, that's a great question. This is indeed something that we're focused on in the unified framework. So with a geometric object, those nestedness actually, I'm sorry I forgot to put the pictures here, but the nestedness is essentially going to be filling all these different the same facets on a hyperdimensional cube, while now the turnover is going to be filling different facets. So geometrically, it's actually provide the different processes in what they're doing. I'm sorry I forgot to put the figures there, but it's actually nestedness on the same facet, while the turnover is on different facets.
That was awesome. Thanks very much for that talk.
Thank you.
I have a question about the part about similarity.
Yeah.
And I'm just wondering practically how you think people can come up with a value for that similarity between 0 and 1.
Yes. So one thing we can do is measure the genetic similarity. So how similar the genetics are between these two species. Another way that people do it is not the similarity, but like functional complementarity. We have been doing a lot in the biodiversity ecosystem functioning literature, where they can measure how much by adding these two species together, the ecosystem functioning can change. And we indeed have some. So a key difference between the similarity and functional complementarity is that, one second. Is now that the off-diagonal values can be negative because it represents the functional complementarity. So instead of compressing the hypervolumes, this functional complementarity can actually expand the hypervolume. So like the joint effects. So yeah, so there are indeed ways to do that in empirical data.
Great, thank you so much.
Thank you all.